So, therefore, this set of functions that we talked about a minute ago is indeed a linear space. That is why I have called it a space here, and we will give that space a name. So, we will call that space V 0. So, V 0 is the set. Now, I am going to write mathematical notation. V 0 is the set of all x of t such that two things happen. X of t, now you know x is a function. So, when I write like this, what I mean is I am suppressing the explicit value of the independent variable, but I recognize that there is an independent variable here, but I am treating the whole thing as an object. It is a function, I am treating the whole function as an object, and this object belongs to L 2 R. Recall that L 2 R is the space of all functions which are square integrable, and this stands for belongs to. So, such that x belongs to L 2 R and x is piecewise constant on all intervals of the form n plus 1, n integer. Now, once we have talked about V 0, and in fact, the reason for giving the subscript 0 here is that we are talking about 2 to the power of 0 as the size of the interval. That is important enough, I think, to make a noting. So, we say V 0 because of piecewise constancy on intervals of size 2 raised to 0, which is 1. And similarly, therefore, in fact, you could call it 2 raised to the power of 0, or you could call it 2 raised to the power of minus 0. We will prefer to use 2 raised to the power minus 0, because it will be consistent in future. So, we could similarly have V 1 then. Similarly, V 1 is the set of all x. Let us define it. The set of all x. X belongs to L 2 R. And x is piecewise constant on standard 2 raised to the power minus 1 intervals. That is intervals of the form n into 2 raised to the minus 1, n plus 1 into 2 raised to the minus 1 for all n integer. And in general, we have V n. The set of all x t. For completeness, we should write down the definition properly. And x is piecewise constant on all open intervals of the form simple enough. To fix our ideas, let us sketch a couple of examples. So, let us take an example of x belonging to V 2. It would look something like this. So, you would have intervals of 1/4 here. And in fact, to be complete, we should also include intervals before 0 and so on. And we have piecewise constancy on these. And so on there. And please remember, x is also in L 2 R. So, when you say it is in V 2, it is automatically of course in L 2 R. And that means that if I take the sum squared of all these constants, that sum squared is going to be finite. That is an important observation. The constants that we assign here must be such that when we sum the square of all of them, magnitude squared of all of them, that sum must converge. This observation is so important that I think we should make a note of it. So, we are saying the sum squared, the absolute squared sum of the piecewise constant values in all these V m must be convergent, and this follows from belonging to L 2 R. Let us also take an example of a function belonging to V minus 1. So, minus 1 means intervals of size of 2 raised to the power minus of minus 1. So, intervals of size 2 and so on there and so on there, and we have piecewise constants there. And so on here and so on there. So, now we get our ideas fixed, what we mean by the spaces V m. Now, the moment we put down these spaces with these examples so clearly, we see a containment relationship. So, there is a relation between these spaces, they are not arbitrary, they are not just totally disjoint and unrelated. In fact, you can notice that if a function belongs to V 0 for example, which means that it is piecewise constant on the standard unit intervals, it is also going to be piecewise constant on the standard half intervals. And for that matter, if a function belongs to V 1, which means that it is piecewise constant on the standard half intervals, it is automatically going to be piecewise constant on the standard 1/4 intervals. To exemplify this, let me go back to this example of x belonging to V minus 1 that I have here. Notice that this function is piecewise constant on the standard intervals of size 2. So, obviously, if you take the standard intervals of size 1, for example, 0 to 1, 1 to 2, 2 to 3, 3 to 4, minus 2 to minus 1, minus 1 to 0 and so on, the function is still piecewise constant. So, therefore, a function that belongs to V minus 1 automatically belongs to V 0. A function that belongs to V 0 automatically belongs to V 1, and therefore, there is a ladder of subspaces that is implied here. What is that ladder? The space V 0 is contained in V 1, the space V 1 is contained in V 2 and so on this way, and of course, the space V minus 1 is contained in V 0, the space V minus 2 in V minus 1 and so on. And we expect intuitively as we move in this direction, we should be going towards L to R. Of course, it is an important question what happens when we go in this direction. That is interesting. We will spend a minute now and reflect on that. So, you see what happens when we go leftwards. What I mean by that is, of course, you have V 0 contained in V 1, contained in V 2, and then V minus 1 contained, contained in V 0, yes, and so on here, so on there. What happens when we go this way? What do we think should happen? What are we doing? We are taking piecewise constant functions on larger and larger intervals. Let us write that down. So, piecewise constant functions on larger intervals. Now, you see, what is the L2 norm of functions as you go leftwards? What kind of a form will it have? It is going to have a form like this, summation on n. Now, you see, remember, the L2 norm is the integral of the absolute squared of the function. And please remember, the function is piecewise constant. So, you have one constant, let us call it C n on the nth interval, and the interval is of size 2 raised to the power minus m. So, this is essentially, you are talking about integrating mod C n squared, it is a constant over an interval of 2 raised to the power minus m, and please remember m is negative and m goes towards minus infinity as you go leftwards. So, that is the same thing as 2 raised. Now, you see 2 raised to the power minus m is 2 raised to the power of mod m in the context of negative m, and summation on m mod C n squared. Now, you see, the subtle point is that if this needs to be finite irrespective of how large m is, we have no control on this except that this part must be finite. But then when we say finite, if it is non-zero and if we allow m to grow without bound, this is going to diverge. So, the only way in which this can converge, no matter how large, large in the sense large in magnitude, how large in magnitude m is, no matter how large in magnitude m is, if this is to converge, then this must be 0, a very important conclusion. So, you are saying that if 2 raised to the power mod m summation n mod C n squared must converge, no matter how large or how negative. Then we must have summation over n C n squared tending to 0. So, essentially what we are saying is, as we move leftwards, we are going towards the 0 function, a point that takes a minute to understand, but is not so difficult, as you can see. So, now we have very clearly an idea of our destination as we move up this ladder towards plus infinity, and as we move down the ladder towards minus infinity, and we can formalize that. What we are saying is, moving upwards. Now, you know, one has to use proper notation. We would have been tempted to say something like limit as m tends to infinity or plus infinity or something like that, but you see, it is not really correct to talk about limits of sets. So, we need to use the notation that is appropriate in the context of sets, namely union. So, when we take a union of two sets, and if one set is contained in the other, we are automatically taking the larger set. So, moving upwards is attained by using union. In other words, we are saying the union of V m, m over all the integers, should almost be L to R. Now, that is where the little catch is. I mean, we would have been happy to write is equal to L to R, but we need to make a little detail here. We need to put something called a closure. I will explain what I mean by a closure. Suppose you were to visualize L to R to be like an object with a boundary. So, suppose this were L to R, just notionally. And this is the boundary of L to R, so to speak. So, it is a space, Now, what we are saying is, as we go in union, that is union m over all integers of V m, it would cover all the inside, covers all the interior. But then it might leave out some peripheral things on the boundary. So, it may also cover some part of the boundary. Now, of course, do not ask me at this stage what we mean by boundary and interior, save that you are talking about situations, boundary. Now, informally when you say boundary, you are talking about functions where moving in a certain direction does not remain L to R, moving in the other one does. So, it's see this boundary and the interior at the moment needs to be understood only informally. But what we are saying is, as far as this union goes, it can take you almost all over L to R, it covers all the interior. It may also cover quite a sizable part of the boundary, but it might leave some patches of the boundary untouched, and therefore, when we do a closure, we are covering up those patches. What we just did was covering up those patches. So, closure means cover up boundary patches. Now, this is a small detail, and we need not spend too much of time in reflecting about this idea of closure and so on, but to be mathematically accurate, we do need to note that it is after closure that the union over all m integer of V m becomes L to R. Otherwise, it is almost L to R, which means that when you take this union, that is when you make piecewise constant approximations on smaller and smaller and smaller intervals, you can go as close as you desire to a function in L to R. So, you can reduce the L2 norm of the function to 0. So, if you look at it, that is what we mean by, that is what is implied by boundary. You know, you can go as close as you like to a certain function. You can make the L2 norm 0, but still it would not quite reach there. So, you know, you could just visualize that you might just be a teeny weeny bit inside that boundary, but not quite on the boundary. And how teeny weeny? As small as you like. That is where the union takes you. That is this subtle idea of closure. Anyway, as I said, we do not need to spend too much of time in talking about this closure, but we should be aware of this idea, because when we read literature on wavelets, or for that matter, when we really wish to put down the axioms of multi-resolution analysis properly, we must be aware that this closure is required. So much so. Anyway, now let us take the second of our inferences here, moving downwards, so to speak. So, how would we move downwards? Just as union takes you upwards, intersection takes you downwards. So, if you take an intersection on all m belonging to Z of V m, there I do not need to worry about closure or anything of that kind. I can simply put down, this is a trivial subspace, essentially the subspace of L 2 R with only the 0 function included. This is called a trivial subspace. Now, again I must make an observation here to clarify. The trivial subspace is not the same as the null subspace. The trivial subspace has only the trivial 0 element in it. The null subspace does not have any element. So, that is a subtle distinction, and we must bear in mind that we are talking about the trivial subspace here.